Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everybody. And I hope you are doing well today. So we will continue our lectures regarding the chapter 4 alkenes. Last lectures we already discussed about the naming of compound, and second one we already discussed about the properties of alkenes, whether they can alkene in generally can dissolve in organic solvent and cannot dissolve in water because the ability that this functional group make a hydrogen bonding with water. This is the main reason why alkenes, most of the alkene cannot do hydrogen soluble in water. So we already proceed a little bit about the Newman projections, how it's important how to draw the Newman projections. And we start with with propane, and now because I have the model here for today, so it's good to have and continue to discuss about the cyclobutane with the fourth member ring. Okay, so in Newman projections, an energy minimum and maximums occur every 60 degrees when it rotates. Okay, 60 degrees until it going back to original conformations. Okay, they have two types of conformations: eclipse and also staggered. Okay, and conformation, as the conformation change from staggered and eclipse, it always rotate without not stop. Okay, because this doesn't have any pi bond that make it stop from rotations. So conformations are neither staggered or eclipse. Okay, we know this one is staggered. The most stable one is staggered. We take carbon number 2, carbon number 3 as a reference. Carbon number 2 at the front, carbon number 3 at the back. Okay, it can represent by this figure. Okay, by this one. Okay, and there are 6 different conformations. Okay, they are always rotate. Okay, so and the butane and high molecular weight alkene have several carbon bonds, all capable of rotations. Okay, and they have 6 conformal difference. It's easy. 360 divided by 60 is become 6. The first one is anti, like this. We have 2 CH3 here. Okay, 2 CH3 in 180 positions. Okay. Okay, anti. This is the most stable one because the 2 CH3, because 2 CH3 is further apart about this one. Doesn't have any interactions because CH3 have another cloud for 3 hydrogens and also 1 carbons. Okay. And when it rotates, okay, it rotates. In this case, they are rotate, okay, rotate. Then the rotate is become eclipse. From staggered is converted to eclipse. Okay, in this time, the CH3 is aligned with hydrogens. Okay, let's see how it's represent. Okay, you can rotate at the carbon number 2 or carbon number 3, and you can easily rotate. Okay, this one is eclipse. Okay, and when they are going to stagger again, okay, staggered again. Okay, okay, this one is staggered. You can see 2 CH3 here. It's close together. Okay, and we rotate again. This one we call gauge. Okay, because the staggered gauge, because it's close together. Okay, almost close together, but it should form in staggered conformer. And after that, we proceed with another 60 degrees, and it's become eclipse. Okay, eclipse. How to do that? Eclipse. Okay, like this. Okay. When it become eclipse, rotate again. it going back to the second conformer for the staggered, for the gauge. Okay. And lastly, they are rotate again and form eclipse. And lastly, when they are going again to another 60 degrees, and we'll give you the staggered conformer. Okay, I hope it's clear. Okay, try to playing around with the Newman and also eclipse. Newman projections, which is staggered and eclipse conformer. Okay, so okay, staggered conformations, which is they have two staggered conformer. If we take an example for this for butanes, they have a few. They have three staggered conformer. I can label this one as A, this one as B, and this one as C. Okay, I hope you can see it. There's the problems, man. Okay, so it will give different energy. Okay. So for the staggered conformation with two large groups at 180 degrees, which is referred as structure A, okay, we call NT. Because the bulky groups, 2CH3 here, is around 180 degrees further apart. Okay. The staggered conformation with two largest groups at 60 degrees, like this, still a staggered, but 60 degrees, okay, we call gauge. Okay, they have, for this one, we have B and C. Okay, and staggered formations, okay, we have two conformers. One is eclipse, another one is staggered. Okay, staggered is the lowest energy compared to eclipse. Okay. Okay. Okay, for the static change, the relative energies of the individual staggered conformation depend on their static change. Okay, so static change is an increase in energy from when non-bonded atoms are forced too close one another. It means in this case, we have eclipse conformer, okay, which is referred as this one, number 4. Okay. Okay. Gauge conformations are generally high in energy than anti-conformations because of static change, because of these two CH3 here. Okay, they have static change. Okay, so because of two CH3 here. Okay, I hope you can see the figure here. Okay, so this one we call steric change, steric strain. Okay, so for conformation of energy of butanes, okay, we have 6 conformer there, and we can align with the energy diagram here. So we know that we have what? We have staggered and also eclipse. Okay, okay, we have staggered or eclipse. Okay. Eclipse. Okay, sorry for my handwritings. So we know that staggered is a more stable compared to eclipse. Okay, so we know that this one is staggered, this one is eclipse. Okay, meanwhile this one is staggered. Okay, this one is staggered. This one is A, this one is B, this one is C, and this one is okay. Okay. Don't forget, if you want to draw the energy diagrams for this one, so don't forget to energy axis X and Y, energy versus tetrahedral angles. And we know this one is the most stable one. Okay, number A is the most stable one compared to the B and C. So this one is the lowest one energy. Okay, because the bulky groups, I can see the bulky group CH3, both CH3 is further apart around 180 degrees. Okay, and this is the anti-conformer. Okay, and meanwhile this one is staggered, but its gauge is around 60 degrees. Okay, in this case, this one only, the degrees is between these two bulky part is around 60 degrees. Okay, this one is 180, this one is 60 degrees. Okay, and for the eclipse, we know eclipse is less stable compared to staggered. So we have a few types of eclipse. Okay, this is what I call one Romans. Okay, this is also one Romans because the arrangements of conformer is quite similar. And we have interactions, okay? For the sterics, they have only interactions between CH3 and also proton only. Okay, it means it's like this. It's like this, okay? Okay, we have interactions between hydrogens here and also CH3. So that's why it's the less stable, okay? Compare that another conformance. Okay, so for the one Romans is the less stables. Okay, and lastly for the fourth one, why a number fourth one I can label it for the two Romans is the most least stables. Okay, because they have steric strain, but the problem is the steric strain is among two CH3. We have two CH3 here. Okay, the difference there. Okay, I hope you understand. Okay, try a little bit more exercise there. I think they have a few exercises there. So I'm repeat again, staggered is more stable compared to eclipse. Staggered have two types. One is anti, and another one is gauge. Anti is more stable compared to gauge because the big groups, the bulky groups or big groups, it's 180 further apart, like this. Okay, and meanwhile for the gauge is only 60 degrees. 60 degrees. I don't know how to show it. Yeah, I think so. Where is my black paper? Sorry, I don't have the black on my hand, but partial black. So okay, again, okay, staggered is more stable than eclipse. Anti is in staggered, eclipse in staggered, anti is more stable compared to gauge. Okay, because of these positions of the bulky groups. I can tell you about the bulky groups only. Okay, for the eclipse, they have we can see the arrangements here because of the strings. Okay, so because of that, they have for example, for this one number one Romans, they have two number one Romans here. They have interactions between H protons, okay, and also CH3. CH, okay, for this one, H, CH3 here. Okay. Meanwhile, for the number two, which is number 4 here, we have interactions between two CH3 here. That's why it's the most least stable. Okay. Okay. I'm slow about this one. I'm going slow. It's better. Okay. I hope it's okay for you. So we will. I will give you a few exercises after this, and we will discuss tomorrow, hopefully. Okay, if we have the time. So barrier to rotations. Drop this one first. Okay. So okay, this is a kind of summary for torsional and steric strain. Okay, so you don't have to memorize the values, so at least you know the theory, it's enough. Okay, which one is the most stable, which one is the less stable. Okay, Okay, energy difference between lowest and higher energy conformations we call barrier to rotations. Okay, so zigzag skeletal structures, since the lowest energy conformation has all bonds staggered and all large group anti-alkanes are often drawn in zigzag skeletal structures to indicate this. Okay, usually we are using skeletal structures when you are going to higher levels. Okay, and you will use frequently the zigzag structure. That's all. Okay. So angle strain in cycloalkanes, beside torsional strain and steric strain, and the conformation of cycloalkane are also affected by angle strain. Okay, I will give you a few examples for the cycloalkanes, and we will try to discuss tomorrow. Because the question is in my another laptop at my office. I will prepare that one later. Okay. So angle strain is increased in energy when bond angle deviated from equilibrium tetrahedral angles around 109.5 degrees. Okay, and cycloalkane is more than 3 atoms in the ring are not flat molecules. Okay, and they are packed to reduce the strain. Okay, 3 to 10 carbon cycloalkanes. Okay, the ideal usually we have 6. But it can be more, okay, for the cycloalkanes, okay. So this is kind of draw an orientation for this kind of compounds, okay, for the cyclic compounds. For cyclohexanes, we are going into the new topic, cyclohexanes. Okay, in reality, cyclohexane adopt the packed chair conformations, which is more stable than other possible conformations. Okay, and for the chair conformation is also stable because it eliminates angle strains, because for the cycloalkane they have to follow 109.5 degrees in tetrahedral form. That's why they are formed in chair conformer. Okay, if you realize also, if you see clearly, this one should be all hydrogen is on stackets, right? For example, like this and like this, you can see from this side. Okay, you can see what's happened to this. Okay, so this one is Y front. This one is in the back. Okay, hydrogen. Don't forget to draw hydrogens here. This one connect with another carbon. This one connect with another carbons. Okay, if we see from this side. If we see from the back, usually no, we see only from the side. In front, it's good. It's different. If you see from this side, you have to do more works to imagine. Okay, so the proton will be. Okay, this one is okay, this one is connected to another carbon, okay, which is carbon here and here. So, okay, so it's depend which angle you want to see. Okay, I strongly advise you see from here to reduce the mistake. Okay, if you insist and sorry that I want to see from this side, go ahead. Okay, it's you will do a mistake when you try to do from another side, okay, because it's quite harder. You have to use your imagination to do that. Okay, in cyclohexane, 3 carbon are packed up, 3 carbon are packed down. Yes, of course, and alternating around the rings. Okay, so if you see clearly here, I will see another examples here. Okay, axial and equatorial, they have 2 terms that you have to understand: axial and equatorial. Okay. Each of cyclohexane have 2 different kind of hydrogens. Okay, axial hydrogen located at above and below. This is axial. Remember this one. And equatorial hydrogen located in the planes. Okay, this one. Okay. And how to draw the cyclohexanes? Okay, for first you have to draw the carbon skeleton here. Okay, so the second one, label the carbon up and carbon down. So this position is carbon down. This position in carbon up. The second one, the third one, draw the axial hydrogen atoms. Okay, axials. We have 3 up, 3 downs. Okay, you have to go back to the definition why it's axial protons. So in this case, we have 3 up and 3 down. So 1, 1, 2, 3 up, 1, 2, 3 down. Okay. So number 4, draw the equatorial atoms. Okay, protons. So we have 3 equatorial up and equatorial down. Okay, so we have this one. Okay, equatorial up is this one. Equatorial down is this one. Okay, so you have to complete everything by following equatorial and axial position of protons. So conformation change, ring flips. Okay, cyclohexane undergoes conformation change that we call ring flips. It means it's not. I should prepare the model. Maybe I will do it later about this one. So we call ring flips. So it's mean from one conformer, okay, this one, conformer number A, we can easily flip down. It's mean we pull this carbon to down and pull this carbon to up positions. Okay, so suddenly if we label this one carbon number A and number 1, okay, if we flip down, it's become like this. So carbon number 1 is become in these positions, and carbon 1, 2, 3, 4, carbon number 4. Carbon number 4 in upper positions. Okay, this is what we call flip down. If we are doing flip up again, okay, it's going back to the A conformer, A and B conformer. Okay, this is very important because from here you can determine which conformer is the most stable one, with which change conformations is the most stable one. Okay, we will discuss later about this. So as a result of flip rings, the up carbon become down. Okay, and down carbon become up. Okay, in these positions, if we flip up, usually I call them flip down because we have to pull this one going down. So from this one, this carbon number 1 have to go down. Carbon number 4 is have to go going up. Okay, and for this one, it's different. Okay, in these positions, it's already if we pull this one number up, carbon number 1 have to going up, carbon number 4 have to going down. We will do more exercise about this one to make sure everybody understand what is called flip up and flip down. Okay. So there are 2 possible chain conformations. Okay, the equatorial position has more rooms. Equatorial, yang duduk luar ni. Okay, okay, equatorials. These positions. Okay, this one is equatorial. Equatorial have more room than axials. Okay, axial in these positions. Axial here. Okay, And the large substituents, this is the key point, large substituents are more stable. If you find the bulky groups, the big groups, it's not hydrogen, a big group, for example, CH3, halogen groups, or the branch structures, okay? So you should put that one in equatorial positions because they have more room compared to axials. Okay, if you see clearly, you have 3 axial up, 3 axial down. They have still interactions. So for example, we have 3 here. Okay, we have interactions. We have hydrogens here. They still have interactions among the protons. For example, if you have a chlorine here, for example, you have chlorine here, for example. So they still have interactions among the protons that we call, we will learn later about this one. Okay, that's why for the bulky groups, the large substituents, we usually prefer to put in equatorial positions. Mark this word, okay? Bulky group have to put in equatorial positions. So cyclohexane can also exist in both conformer. We are not interested to discuss this one, but this is another conformer in between. If you want to convert one conformer, chain conformer, and after that you flip the structures in between conformer A, chain conformer A, then chain conformer B, they are the both conformer, but it's not really stable. Okay, both conformations of cyclohexane are 7 kilocalvin per mole less stable, okay, than chain conformation. That's why in generals they are preferred to go to the more stable one. Okay, but conformation is destabilized by torsional strain because the hydrogen of 4 carbon atoms are placed eclipse. Okay, because we know everything's preferred to form in staggered. You have to go back to the first statement here. Yes. Okay. Cyclohexane prefer to form in staggered, but both prefer to force to rotate in eclipse. Okay, additionally, there are steric strain because 2 hydrogen at the end of the boat. Okay, this one. Okay. Are forced to close each other. Okay, that's why it's not really stable. Next, okay, how to drawing the substituted cyclohexanes. Okay, first, by following the same rules that we learned how to draw the cyclohexanes. So first draw the chain conformations and add substitutions. So you have to understand that they have 6 axial, 6 equatorial, in axial 3 up, 3 down, okay? So, and after that, you have to put the bulky groups in equatorial positions, okay? The second one, flip of the cyclohexane ring. You can flip up and flip down, okay? Okay, it's not flip like this, you know. You have a paper like this, you flip like this. It's not flip, okay? You have to pull the carbon from here. Okay, pull going down, and this carbon will going up. This carbon will going up. This carbon will going down. Okay, and you can create the second conformer. Okay, so for the third one, add the substitutions at the second conformations. Okay, in this case, you have to change. Okay, previously it's okay. In the first structures, if they are in positions axials, okay, when it flipped, it's become equatorial. Okay, if they are equatorial, it can be axial. Okay, for example, like this. Okay, this CH3 is equatorial positions. Okay, by using these rules, it's become axial. Okay. So chain conformation and energy, the two chain conformation of cyclohexane are different, so they are not equally stable. Yes, okay. So the large axial substitutions create destabilized, thus unfavored, that we call 1,3 diaxial interactions. I will explain why we call 1,3 diaxial interactions. Okay. In this one, in methyl cyclohexane, each unfavored HCH3 interaction destabilizes the conformations by 0.9 kilocalvin per mole. So conformation 2, okay, conformation B is the less stable than conformation 1. Okay, what they said about this one. Okay, this one is the first conformer we call conformer A, and we are doing flip structures, flip down. We are doing flip down. And this one is going up. So we label this one as carbon number 1, and we are doing flip down. We pull the carbon to going down. Okay, from this shape of conformer, we change to this. Okay, in this time, the carbon number 1 is become at these positions. Okay, by using the rules that I had said, axial, we go to equatorial, and equatorial, we go axial. So this one is equatorial positions. Carbon number 1 is here. Okay, I will hold it here. So when we pull down the carbon, okay, so the carbon is become like here, it's become axial. Okay, why conformer A is more stable compared to conformer B? Because conformer A, they have 1,3 diaxial interactions. Okay, again, I said they have proton here, they have proton here. This is why we call 1,3 diaxial interactions. 1, 2, 3, okay, 1, 2, 3, 1, 1, 2, 3. That's why we call diaxial interaction. If another CH3 here, they have another 2 diaxial interactions. Okay. Okay, I hope it's clear. Okay. Okay, preference of equatorial positions in substituted cyclohexanes. Okay, 3-dimensional representations for 2-chain conformation in methyl cyclohexanes. Okay, so this is explain why we are prefer to put the bulky groups or the substitutions in the equatorial positions. This is represented by the ball and stick model. Okay. So preference of equatorial position substitution is working. Okay, the largest substituents. Okay, the largest substituents on the 6-member ring is higher presence of equatorial conformations. For examples, okay, this we have third butyl group. This huge groups, and they are not they are highly destabilized, because if we can imagine, so they have another branch for hydrogens. Okay, that's why they are prefer to form 100% in by putting the third butyl group in equatorial position. It's almost impossible to form in this axial third butyls. Okay, because they have a huge interactions between this third butyl group together with hydrogens. One. The second one is very crowded. Okay, that's why they are not preferred to form in axial positions, but they are preferable to have in equatorial positions. Okay. Okay, this is the explanations for this one. Okay. Okay, for the disubstituted cycloalkanes, okay, there are two difference. One, two dimethyl cyclopentanes, one having two CH3 groups at the same sides, and one having them in opposite side. Okay, this one, in this case, we are going into the isomers. Okay, so one is we call the cis isomers because it's similar conformers. Okay, and another one we call trans isomers. The position of CH3 is different. Okay, yes, and A and B we can call stereo isomers. Okay. Okay, stereoisomer that differ only in way of atom oriented in space. Okay, so prefixes and trans are used. Okay, distinguish these isomers, and cis isomers are two groups in the same side. Okay, meanwhile trans isomers are opposite side. Okay. So this is kind of simple example for cyclopentane here. Okay, we have cis and isomers, and this one is a stereoisomers. Okay. For a disubstituted cyclohexane, okay, such as this kind of compound 1,4-dimethyl cyclohexanes, okay, has also cis and trans isomers, and it's also stereoisomers. Okay. Each of these stereoisomers has two possible conformations. Okay, and how to draw it? Everything is about drawing. Okay, so draw that one chair form and add the substitutions. Okay, for the trans, okay, you should have different angles for this one. Okay, second one, flip the ring of cyclohexane, similar that we have done before. Okay, you have to draw the conformer. Okay, from A, you choose the A conformer first, put the substitutions, okay, correctly, and after that you have to do the same thing, draw the conformer number B, whether you pull up or pull down the cyclic ring. Okay, flip, doing flip. It's not like this, you just pulling there. Okay, in this case, for example, we label this one carbon number 1 and carbon number 4 here. So carbon number 1 become down, carbon number 4 will be up. And after that, you have to put the substitutions. Okay, in this one, you have to put using axial, will become equatorial. Equatorial become in this. Okay. Okay. For the trans disubstituted cycloalkanes, you have to know trans is in different orientations. Okay. What we can summarize in this one, we can put like this, up. Okay. Up, up, down, down, cis, up, down, down, up. Trans. In this case, for the trans compounds, this one is up, this one is down. It's correct. Okay, and check again your answers. Okay, this one is down, this one is up. Trans. Okay. Okay, so And after that, you have to determine which one is more stable. So you have to go back the original rules, okay? Put the bulky substituents equatorial positions. In this case, we have two CH3 in axials, another two in equatorial. So this one is the most stable one because the bulky group doesn't have any interaction with. They have more room, to do that. Okay. For this one, why diaxial is not really stable? Okay, because they have they have 2,1,3 diaxial interactions. Okay. Oh, sorry, it's already do some explanations here. Okay. So for the cis isomers, okay, cis isomers, both up or both down. That's why I'm using up, down, down here. See this one. That's why I'm using this. Very easy for you. Okay. So for example, we have conformations 1, 2, 1, and 2. Have two CH2 group draw up. Okay. For up positions. Okay. This one is up, cis. Correct. Okay. And when we try to do flip structures again, okay, for example, carbon number 1, and if we flip down, okay, and this one become up, carbon number 4 here. So this one carbon number 1, this one is carbon number 4. Okay. So both conformation have one CH3 axials. Okay. This one is axial. This one is equatorial, and this one is axial, and this one is equatorial. Okay, 1 to 1. Okay, this is have 1, 3 diaxial. This one also have 3, 1 3 diaxial interaction. So this is a equally stable. Not much difference. No different at all. Okay, it's equally stable. That's why we're using this kind of arrows compared to this one. Okay. Okay, oxidations and reduction reactions. Okay, oxidation result in increasing number of Zigzag bond. Meanwhile, oxidation also decreases the number of CH bond. Okay. And reduction decrease the number of Zigzag bond and also increasing the number of CH bond. Of course, reduction we add more proton to them. So that's why you have to understand about oxidation and reduction reactions. Okay, we will learn about this one in chapter 11. I think chapter 7 to 11 soon. Okay, and this is the simplest way how to understand about the oxidation and reduction. Increasing number of oxidations, it will increase the number of CO bond, decrease the number of CH bond. For the reductions, they will vice versa, decrease the number of CZ bond, increase the number of CH bond. For the combustions of alkanes, okay, alkanes undergo combustions. For example, the easiest way is petroleums, okay, gas that we use for kitchens, okay. They will burn in presence of oxygen. They will give you carbon dioxide and water. This is the example of oxidation reduction reactions. Okay. Nothing important about this one. Is just give you an example about the oxidation and reductions. For the lipids, okay, anybody who are from biological schools, you are playing around with these biomolecules. Okay, lipids are biomolecules that are soluble in organic solvent and insoluble in water. Okay, why? This is the reasons. Okay, compose many non-polar, CH and CCA bonds, but fewer polar functional groups. Okay, you have to refer back chapter number 3. Okay, the limit is until carbon 5, 5 carbon only. So, and after that, you have to check whether this kind of compounds have a higher solubility or not. Okay, for example, the easiest example here, the component in BVAX. Okay, they have a huge number of non-polar, but they have only these functional groups. Okay, they can make the hydrogen bonding, but not much compared to the van der Waals. Okay, so another example is cholesterol. They have a huge number for the non-polar part, and this one is only OH for the polar part. Okay, it means they are only soluble in non-polar solvents. Okay, inorganic solvents in general. Okay, cholesterol is a member of steroids of family, groups of lipid having 4 rings joined together, and because there has one polar OH group, it's insoluble in aqueous media of the blood. That's why our fat not dissolve in our body. Okay. So, and they have hydrophobic and hydrophilic areas. Okay, so I think that's all for chapter 4. Okay, what we have learned today is we continue with the drawing the Newman projections for cyclobutanes. Okay, so and after that we're going to discuss about the Che conformer. Okay, why Che conformer is more stable compared to both conformer, because Che conformer we have to form in staggered. Okay, meanwhile for the both we have to form in eclipse. So staggered is more stable compared to eclipse. That's why it's favorable to follow in staggered. Okay, and after that we learn how to draw the Che conformers and how we can do the flip structures. Okay, it's not flip like this. Okay, it's pulling the carbon to going down, and automatically another groups of carbons will going up. So this is the in Che conformer they have 2 conformers, conformers A and conformer B. Usually we love to draw the stable conformers for these cyclic compounds. You have to draw both actually. Okay, first draw one structures, conformer A, and after that you're doing the flip structure of conformer A, it become conformer B, and from this one you have to determine which one is the most stable. Usually I think last 3 years we ask this kind of questions, and it's 3 marks. Okay, first conformer 1 mark, second conformer 1 marks, and you have to conclude which one is conformer is more stable is 3 marks, another 1 mark, so overall is 3 marks. Okay, so and again so you have to determine the compound or draw the compound is cis or trans compounds. Okay, for the cis compound is as up or down downs. For the trans is up down and down ups. Okay, if you want to do the flip structures, you have to bear in mind if the conformer A, the axials is become equatorials and equatorial become axials. Okay, I think that's all for today. We already cover up everything in chapter 4. Okay, maybe tomorrow we will start to discuss about question that I've given to you, and I will put more question in e-learning after this, after I arrive to my office. So hopefully we can see and discuss tomorrow, hopefully. Okay, I think that's all for today. Thank you very much, and stay safe, stay healthy. Okay, and Assalamualaikum warahmatullahi wabarakatuh.
Yes, come on, shorty, let's go. Girl, I see you over there in the corner of the dance floor, and I know you're acting shy, looking at the corner of your eye. So I pick my heart closer to yours. Catch my breath and I say, I'm the one you're looking for. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance and just one glance. So don't wait no more, I'm me, I'm more. I'm the one you're looking for, shorty. Oh, girl, I see you over there hesitating, deliberating. You keep me waiting on a sign, looking at the corner of your eye. So I pick my feet up off the floor, move my hips closer to yours. Catch my breath and I say, I'm the one you're looking for. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance and just one glance. So don't wait no more, I'm me, I'm more. I'm the one you're looking for, shorty. I'll be the one you're looking for, shorty. So come on the dance floor and baby show me all your moves, all your grooves. Shorty, I got something to prove to you. So come on, take a little chance. Got me in a trance and just one glance. So don't wait no more, I'm me, I'm more. I'm the one you're looking for, shorty. So come on, dance a little dance, dance a little dance. Come on, dance a little dance. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance and just one glance. So don't wait no more, I'm me, I'm more. I'm the one you're looking for, shorty.